Alrighty guys, this is going to be your concept map video for circular motion. I'm just going to kind of ramble on about a bunch of different things pertaining to circular motion. I'm going to do a second video about gravitation, just that way this video isn't super long. So make sure you pay attention to that. There's a second video kind of pertaining to this unit. So the first thing we're going to talk about is, let's take a real big step back and just talk about speed. Speed is distance over time. And so the path which an object travels divided by its time. And so if we look at this in the concept of an object traveling in a circle, let's see, we'll erase that inside just a little bit. Just talking about an object traveling in a circle around another object. This object on the outside, its distance it's gone has been the circumference of a circle. And remember, the circumference of a circle is 2 pi r. So if we look at the speed of an object traveling in a circle, we can say that the distance it's gone is the circumference. So speed equals 2 pi r over the time it's taken that to go. Now, speed is a scalar number, and it often doesn't denote direction. But what we do is in physics world, we denote this as centripetal velocity, or v sub c, being 2 pi r over t. Now, this is not a formula that's given to you on your reference sheet, so it's just kind of expected for you to understand the basics of speed and velocity and being able to denote what that looks like. So from there, we can go to the next step, which is mentioned on your reference sheet, and that is then acceleration. So we say acceleration is the change in velocity, and so what we denote that centripetal acceleration is the change in velocity over your change in time. However, this doesn't necessarily compute super well when you're looking at linear and angular components. And so what we do is we just go with the assumption that you don't need to do the derivation to go from linear acceleration to centripetal acceleration and all those proofs in between. What is given on your reference sheet is centripetal acceleration is centripetal velocity squared over r, and r being your radius of the motion. From there, since we look at centripetal acceleration, we're able to say that because your object is constantly moving, so it's constantly turning. So what we say is, because centripetal velocity is constantly changing. And that's just because it's changing direction, not necessarily changing in its speed or its magnitude. And what we can then say that if radius is held constant, if r is constant and centripetal velocity is constantly changing, that your centripetal acceleration is going to be constant. So what we denote is the overall speed doesn't change, but your velocity does, because you're always changing that direction. So make sure when you're talking about these ones, you don't use vague terms like speed, because when you say speed, you also need to include that the magnitude doesn't change with direction. So how do we go from acceleration to force? So let's go on that next step there. But before we do that, let's talk about what the word centripetal means. Centripetal. And so what we say is that this word is centri, which means center, seeking, meaning its acceleration is always inwards. So if I were to go back up here to my image, the acceleration value here would always be pointing inwards, because that object is always curving towards an inwards direction. So let's really unpack. Let's zoom in just a little bit closer up here and really unpack that. So if I were to look at this object's velocity at this given point, it is going in this direction. It is tangential. So its centripetal velocity is tangential. Acceleration is always going inwards. So when this object continues along this path and is right here now, we say then that that centripetal acceleration is still inwards and that that velocity is still tangential, because that velocity is always curving towards the inwards. That object is then center seeking. Alrighty, so let's move on to the next thing. What can we do with centripetal acceleration? This is a formula not given on your reference sheet, and it's nice just to kind of have in your back pocket. If you look at Newton's second law, which is F net equals ma. If we put this in terms of circular motion, we then say an object traveling in a circle, its net force, or its centripetal force, would be its mass times its centripetal acceleration. Or if we use that value for what we get for acceleration, that'd be mv squared over r. And that's because we said centripetal acceleration is v squared over r earlier. Okay, so what do you do with F net? F net, is it ever drawn on your free body diagrams? Well, that answer is no. And so, never drawn on free body diagrams. It then helps you determine your algebra later on, but it doesn't necessarily help you within that moment when you're drawing your free body diagrams. Every once in a while, you'll see a word being used called centrifugal. Now, centrifugal forces aren't necessarily talked about in this class because what is assumed to be is your frame of reference from the inertial mass. So centrifugal forces is a change in frame of reference. So they're not really ever mentioned in this class, and they're often used just to trip you up. So as far as centrifugal forces, don't really put too much stock into them because they're an assumption not taken in AP Physics 1. All right, what do we have next? What do we do with a free body diagram of an object traveling in a circle? So let's do that. Let's take our object. Let's go ahead and let's just draw a circle. About the best I can. Let's erase this little iffy part in the middle. And let's just go from right here. So I've got an object right here traveling in a circle. You could say this is a tennis ball being swung above your head. Doesn't really matter. And so when we draw our free body diagrams, centripetal force does not show up. Now let's erase that real quick. Centripetal force is no show. In the same way you never draw F net on your free body diagrams, you never draw centripetal force. So with that being said, if this object, let's say that this is a tennis ball being swung in a vertical circle. So the same way that some people spin their lanyards. At the bottom of the swing, we have, let's do red. And so at the bottom of the swing, the object has mass. So we're going to call that, this is weight, or you can say force due to gravity. When it comes to what we're looking for on the test, either one suffices. Then you have an upwards force here, and that would be the string holding the tennis ball. And so we call that force of tension, or you can just say T. F sub T or T, either one works. And that is going to be it as far as the forces overall acting on a tennis ball being swung in a vertical circle. So how would you write your equilibrium statements from this? So what we do is we in the same way that we have F net equals ma, when you're looking at a centripetal question, you do still start with the same thing. But instead of saying F net, we're going to say centripetal force equals mass times centripetal acceleration. And what is causing that centripetal acceleration? Well, since the overall force that's causing it to pull inwards is larger, or tension for this case, is going to be subtracted by weight. And so tension has to be larger, because if weight was larger, it would go downwards. And so what would then say is a mass times centripetal acceleration equals tension minus weight. And then depending on what you're looking for, say like, what is the tension in the string right now? You would say tension equals mass times centripetal acceleration plus mass times gravity. And so from there, you can look for whatever you're looking for as far as manipulation goes. If it looks like you ever get to this point and you don't have enough variables, like they give you tension and they give you mass, remember we can also break this down just a little bit and then say mass v squared over r equals tension minus mg. And so from there we can, based on what variables we're looking at, depends on what we're solving for. From there, it kind of gets case-by-case basis on the question, but that's a good start when drawing your free body diagrams and then writing out your equilibrium statements. All right, now let's unpack this just a little bit more and then look at some special cases. So I'm going to scroll this down, and we're going to draw that circle again. So this is, again, just a vertical circle, or an object vertically being spun around. Could be a tennis ball, could be lanyards, doesn't matter. And then down here in the bottom, what is going on at these three different locations? And so what we can then say is, if we look at our free body diagram for all of these, weight is going to be downwards. Remember, you can also say force due to gravity. And then tension is going to be always going inwards. So we got a second force here, and that's going to be tension. And so what we can then say is, depending upon our situation, like if speed is held constant, we can make a couple of assumptions. So let me look here real quick, make sure. Got my reference sheet here. So basically, here's my cheat sheet on what I'm looking for. Alrighty. Let's talk about if tension is constant. Like the value of tension is constant. What does that do to your speed? And so we'll call this, let's do blue. Let's do this, we'll call this instance 1, call this instance 2, and then call this instance 3. If tension is constant in this system, when is the object traveling the fastest? And so what we then say is, at what point is the object allowed to go the fastest without causing other problems like the string breaking? So at the bottom of the string here, we have weight working against tension. And so that is when tension is going to want to be pulled the most. And when are you allowed to go the fastest? And that's going to be at the top here. So the velocity at 1 is going to be greater than the velocity at 2 and greater than the velocity at 3. And this is because the direction of weight interacting with it. If we think of weight going with tension, it is able to go faster. If we think of weight going against tension, it is going to have to kind of go slower in order to keep that tension constant. So let's flip this on its head and say, if velocity is constant, centripetal velocity is constant, what does this do as far as my tension goes? And this one might be a little bit easier to understand as far as how the tension changes if you keep spinning it at the same speed. And so the tension at the bottom is going to have to be the highest in order to keep that speed constant, because weight is working against it, which means at the top, the tension is weight is working with it, and so tension is going to be the smallest, and then tension 2 in the middle. So what from here you say is, if I'm spinning a lanyard, where is it most likely liable to break? And that is at the bottom. So if you're spinning a lanyard around, where is it most likely to break and go flying off? And that's going to be at the bottom of your motion. This is also why when people are using slingshots, and they are, not slingshots, but slings to throw a rock, why they would do it at the bottom of the throw, or softball players at the bottom of the throw. And that's because this allows you to get the fastest speed, because or what's going to allow you to launch the fastest. And that's just because that's where most of the interaction is going on. All right. So with that being said, we're good on vertical. Now, what happens if I start tossing this around in a horizontal plane? So, for example, like a lasso above my head. So I'm going to scroll down here a little bit more. And so if I've got a string, and this object is then going in a circle around a center plane. Let's see if I can do this just a little bit better. So let's do, we got some sort of apparatus. Actually, let's just hang it from the ceiling. That's probably easier. So we got a string hanging from the ceiling, and that we have an object traveling in a circle. Let's see if I can do this, and then we'll just make our object a different color. How about that? We'll make it yellow, and then my object is flying around in a circle. What do we do here? Well, there's a couple things I quickly want to throw out here, is that you're still going to draw your free body diagram, but we're going to do it at the cross section of from here. See how that makes a triangle there? So I'm just going to redraw this triangle. Oh, I'll just redraw that. Hopefully just a little bit better. There we go. Wonderful. Alrighty. And what we could say then is that the tension in the string is upwards. Let me do a black. That way we can talk about this. Is tension from the string is going to be upwards. Weight of that ball is still going to be downwards. And as far as the forces interacting on this, that's it. However, we have something at an angle. And so what we're going to do here is this angle right here, theta, is going to be equal to this angle right here. And I'll kind of explain in a second. Anytime you have forces at an angle, you're going to have to do trig in order to break it into its components. But why is this angle from the horizontal equal to this angle? And that's that back to geometry, alternate interior angles theorem says that the angle between two parallel lines bisected by another line is going to be, those angles are going to be equal but opposite to each other. So every once in a while they like to trick you and say the angle here is some value, and then people make that assumption that it's there, and it's not, unless it's a 45. Okay, so what do we do here? We then redraw our free body diagram. So when it comes to components, always, always, always just redraw your free body diagram. And then in blue here, let's do the components. So we have tension in the x direction, tension in the y direction. And so from here, what we can say then is that tension in the y direction is equal to weight, and that what is causing your centripetal force inwards is tension in the x direction. Okay, so let's unpack this just a little bit and see what we can do here. So tension in the y direction, if this is my angle right here, that's going to be, I'm going to rewrite it over here. Tension in the y direction, that's going to be your angle of sine. So this is going to be tension sine theta. At this point, you should be okay with going from tension in the y direction to jumping to tension t sine theta. If not, that's a big red flag. Come talk to me. Weight equals mass times gravity. And then what about centripetal force? Is going to be equal to t sub x. Well, centripetal force is mv squared over r, and tension in the x direction is going to be t cosine of theta. All right, so depending upon what your question is looking for, you can solve for mass, you can solve for a bunch of different other things, depending upon what your question is looking for. I really enjoy doing this with the Flying Pig Lab, and then not giving students the mass of the pig, determine the time it takes to go around 20 times or so. But anyways, so you can unpack this just a hair bit further. We know that centripetal velocity equals 2 pi r over t. And so be careful not to mix this t with tension. This is the period, so I'm going to do this as lowercase t. We can plug this in right up here and get m2 pi r squared all over r equals t cosine of theta. And since we have t and t over here, you can then also plug these two in with each other if you're looking, depending upon what kind of variables you're looking for. Alrighty guys, and then as far as that goes, I believe that is going to be it. And then we're going to save the next video for gravitational motion. I am going to actually tag on one last thing. What if an object, instead of in the horizontal direction, is spinning on a plate? So I got a plate here, and we got, let's give it like a penny on a record player is often the example I use. If a penny's on a record player, what all is happening? And so we're still going to draw the free body diagram here. So the free body diagram would be, looking at that penny from the side view, we have weight downwards, force normal upwards. But what is causing that object to constantly turn inwards? And that is friction. So if you think about that penny all constantly turning inwards, what is pulling it inwards is friction. And so then when we say then here is that force normal equals weight, and you can say force normal also equals mg, and then we also say frictional force is equal to mu sub k, or sorry, mu sub s, force normal, and that what is your F net, your centripetal force? That is frictional force, which you can then plug in mu sub s, F force normal, and then expand it just a little bit further and say mu sub s force normal, which also equals mg, and pull in mg. So you can say centripetal force equals all this stuff. Now we can unpack centripetal force more and say mv squared over r equals mu sub s mg, and mass will then cancel, and then you can solve for whatever you need to solve. Alright guys, that will be it as far as this concept map goes. You're welcome to do any practice problems you want, but there's some good quick hitting facts about everything dealing with circular motion that I can kind of think of at the moment. Alrighty guys, good luck. If you got any questions, let me know.